Okay, and welcome to video 3. So if you followed in the first video, we went through putting gradient descent together and what we need to do with our x and our y. Okay, in the last video, we put the basics of the gradient descent together. And what we want to do now in video 3 is we actually need to go and work out the cost. So as we're doing gradient descent, we want to keep track of what's the actual cost according to the cost function over here. And then we want to make sure that our cost is actually minimizing as we go through gradient descent. All right, so if I go into here, this is where we're going to do it. So it'll be costs. Okay, so we've got already an array called costs, or a matrix called costs. And we're going to put in R, so in other words, in this particular repetition. And we're going to say, we'll go create the cost function now. And what are we going to pass in? We're going to pass in, what do we need? So we need our x and we need our y and obviously our theta. So let's put in our thetas. So keep in mind gradient descent. We've sent in an initial theta of where all the thetas, theta 0 to 1 is zeros. And now gradient descent has given us a new theta. And now we're trying to see, hey, is the cost, as we go through each of the repetitions, is the cost reducing of those thetas? So, and then we're going to pass in xo, which is our x1s, and our y. Great. So let me go and copy that. Create a new function. And let's call it a cost over here equals cost. All right, and let's say I'm going to call this j. Hey? You can see the cost function normally gets returned as a j, so we'll call it j in here. Save it as cost.m. All right, so you can see our formula that we're trying to get to here. So the first bit is, again, we need our hypothesis. So because we add ones to our x matrix, we got the ones column in front of it. We can actually just multiply these two together, and that'll go and do the formula, the hypothesis formula, perfectly for us. So theta 0 plus theta 1 times x1 for variable 1 or feature 1 plus theta 2 times x2, etc. So it'll do this formula perfectly. So let's go and say our hypothesis equals xo times thetas. Okay, and we'll see it in action with the data in a few minutes. But now what we want to do is we want to minus y. Okay, so again, matrix subtraction will go and give us a hypothesis, a single value for that particular row with those thetas, and then it'll minus from the actual y that was sent in to give us a cost. Great, so now that we've got, we're also going to call it hypothesis cost. So now that we've got that, what we want to do is we want to take HC, which is referring to this bit over here, and we want to square it, and then we want to get the sum of all those squares. So this is known as the squared error function. Now to square it, we know we can just, if we take HOs, I'll show you what I can do here. Let's get at the bottom here. Right, so we can see there's our cost, hey, for the particular theta that we have at that point in time. So let me just say HC, just to replicate what we got at the top. Now, if I want to square this, what I can, and I want to sum it at exactly the same time, what I can do is have a vector times a matrix. Okay, so to make this a vector, I can just add the single quote, and then I can say times a matrix. So that's the same as squaring my results of HC, because squared is just the figure times the figure. Okay, and not only that, it also goes and gives me my sum. So it's dealt with the sum part of it over here. So that's exactly what I'm going to do here. I'm going to say j equals, and we'll fill in the rest later, but it'll be a vector, times the matrix. Great, and that's going to give us So it's going to give us this sum portion over here. Now what I need to do, so once I've summed the results, which is what we've got here, I want to now times that by 1 over 2m. Okay, so m is the number of training examples that we've got. So it's basically the length of y. All right, now obviously 1 over 2n times this result is the same as saying all of this divided by 2m. So that's what we're going to do here, just to make it a little bit easier. And just so that the formula makes sense, I'll say m equals the length of y. That's the number of training examples. So in here, I'm going to say 2 times m. Okay, and that gives us our cost. So there we go. Hopefully all that makes sense. So this bit, or let's say this bit over here, our hypothesis cost, calculates that bit for us, the hypothesis of x minus y. Squaring it and summing it at the same time is dealt with over there. And then 1 over 2n times our sum result is basically the same as 2 divided by 2 times m over here. Okay, so hopefully that all makes sense. So if I go back here now, the cost that I'm going to put into that portion in the array should hopefully come from there. So what I'm going to do is put that at the end here, the break. All right, and once I've got my breakpoint at the end, I'll go back to main and hit the play button. And what I'm looking at now is, let's see, you can see what that's the best theta that our costs have come up with. And if we have a look at our costs, we can see that our cost is reducing on every iteration. So let's go and have a proper look at it over here. And let's see how low our iterations get. So you can see the cost is going down. I think we got 1,500. There we go, down to 0 point something. So the cost is not looking bad, eh? There we go. It's going further down, and it'll just carry on working. The cost just carries on getting less and less, however many repetitions we go down to. But there we go, got down to 0.0175. Fantastic. All right, so far looking good. Okay, let's just now go and plot our costs, and then in the final video we'll actually do a prediction. So at this point I want to plot my costs. So whenever I plot, I've got to give an x and a y. So the x will be the costs themselves, and the y, I'll just create a little array here with, it'll have numbers of 1 to 1,500. Okay, so that's just creating that. So now that we've plotted it, let's go and run it, and let's see if gradient descent is working correctly. All right, and there we go. So you can see gradient descent eventually made its way down to a good cost level. Okay, so if you know gradient descent, when it's too big like this, when it's a fairly big gap, it means that our learning rate is actually too small. So you see our learning rate was 0.01. So I'm going to go and change that to 0.1. Okay, and that looks better. So you see there, we already got to a very low value by, I guess, around about 250 or so. So to be honest, right now, we could actually lower our repetitions. We don't need to go repeat all the way up to 1,500. Okay, so when you do your costs, or when you graph your costs, at least, this is the kind of shape that you want to be looking for. If it's going up in this direction over here, it means your learning rate is too high. So now you might be asking, what if our learning rate is too big? Let's go and give it a learning rate of 4, hey? And what actually happens? And there we go. You can see the cost graph actually gets worse. Okay, so this is the reason why you actually plot the costs, because you want to see that your cost is coming down and that your learning rate is actually correct. Right, and let's just run that once more. And there we go. We're back to a good result over here. And what was our final theta best? Let me just go and print it out for you. So there we go. We've got an intercept at 7.5, and then we've got 2 as the slope. Okay, thank you.